We are discussing about solving optimization problem, and we have discussed one specific problem and used to solve that specific problem the genetic algorithm that we have used. Now, the specific problem in the sense that we consider only one objective function to be optimized. So, one objective function subject to a number of constraints when a number of design parameters are involved. So, this is a special case. Now, we are going to discuss more general cases of solving optimization problem, where instead of only one objective function, there will be two or more objective function. So, this particular problem is called multi-objective optimization problem. Okay, so in a formal notation, the multi-objective optimization problem we may abbreviate as a MOOP, is a short form of multi-objective optimization problem, where we can define in a formal specification which is here. So, like the objective functions related to the single objective optimization, we have understood that objectives, constants and design parameters. So, here we can see the difference between these definition in the context of multi-objective optimization problem. Here the objectives are a number of objectives. In this expression we have discussed about M objectives, and out of these M objectives, some objectives are to be minimized or some are to be maximized, or all objectives are to be minimized or all objectives are to be maximized, and the remaining parts are the same as in case of single objective function. So, there are constants. So, here we have stated L number of constants are involved, and those constants are expressed by the function say g j, and you can say that all the constants are expressed in terms of all the design variables. So, here the design variables which are used to define an ith objective functions are the same design variables are used to define the jth constants, and these are the design parameters, design variables. Now, here I want to see here. So, all these are the constants are related to some another constants are related to some constant, and they are related by this operator. It is called the relational operator. That means, every constant has different relational operators, maybe say equals to, less than or greater than some constant. So, this is the general expression in fact, right, and then the design parameters also expressed in terms of some other relational operators, and they are also related with some constant for the kth parameter. For example, say if x 1 is a one parameter, x is greater than equals to 5. So, this is the one constant. Okay. So, these are the different these are the statements by which we can express the multi-objective optimization problem, and as we have mentioned, it is there for the multi-objective optimization problem, these values of m should be at least 2, and the objective functions are there which are to be optimized either under subject to the minimization problem or maximization problem or both. Now, here I want to say one more thing is that in any objective function which is to be minimized can be equivalently converted to a maximization problem and vice versa. For example, so f x, this is equals to some function x. If this is a problem for minimization, then the same objective function, so it is suppose minimized, then the same function can be started maximize f x, or we can say f dash x equals to 1 by, okay, so it is minimize f x, then f dash x is basically 1 by f x. So, basically which is the inverse of the function is basically maximization. This is another way, another way also we can write, say one function is minimize f x, the equivalent maximization problem can be maximize minus f x. So, both are the same. So, these are the transformation from minimization to a maximization problem. What I want to say is that if there are some objective function are minimized or maximized, then we can express uniformly either belongs to all functions are minimization problem or maximization problem. Now, the statement by which a minimization problem can be converted to a maximization and vice versa is called duality problem. So, we can apply the duality problem to transform the objective function from the form of minimization to the form of maximization. Okay, so, this is about the problem that we MOOP statement of MOOP problem, and having this understanding we will discuss about what exactly the problem it is here. Anyway, so in a more mathematical expression we can tell about the MOOP problem where n number of design variables and m number of objective functions are involved, and without any loss of generality we assume that all objective functions are to be minimized. Then what we can say is that in fact minimizing all the functions or all the objective function will give some results which is basically minimizing one another what is called the combined function. So, we say that f x is a combination of all the objectives that is there, and then these are the output that this combined objective function will return. So, here y is basically an output and all the design variables solution design parameters are the basically input to the problem. Now, so we can decide about in the context of this expression. So, these are the x is basically set of design variables which is denoted here more specifically, and all the values of x which are like this they belongs to some set, it is called the x. Similarly, y it will return the output is objective function. So, all these objective values, and we can term these objective functions the results as an output, and all the value of whatever it is this it will be in the domain, it is called the y. So, x and y are the two domain, we can say it is input domain and it is the output domain. So, for some values of the design variables it will produce these are the output, and so this is there. Now, so here more precisely this x is called the decision vector, and all the small y1 and all this thing is called the part of the objective vector. So, this x is decision vector and y which is basically the results obtained from each function constitute a vector and is called the objective vector, and this x is called the decision space whereas y is called the objective space. So, basically as I know that so far the objective function solving an optimization problem is using genetic algorithm is basically a searching problem. Now, if this is the statement of the problem multi-objective problem, now let us understand what basically to be searched here. I will explain these things with the only two objective function, so that I want to give more graphical impression about the concept. Here in this example, suppose f1 and f2 are the two objective functions. Okay. So, this y is basically is a vector y1, this is equals to f1 x and then y2 equals to f2 x. Okay. So, we symbolically represent this concept y using this expression. So, it is basically idea is that for the different values of f1 and f2 the different solutions are possible, and that is the solution is called this one. So, this is basically an objective vector. So, y is the objective vector here which has the two parts, one f1 part and f2 part. Now, again so far the input space is concerned, that is the decision space. So, this basically represents the decision domain, and here we represent a decision vector in terms of three parameters or values, the x1, x2 and x3. So, the same thing can be depicted in the 3-dimensional space, and so this at any instant this point in the decision space represents the instance of a vector having. So, this is the x1 value, this is the x2 value and this is the x3 value. So, it is like this. So, this way we will be able to express. So, this is the decision space and this is the objective space. Now, so for the searching of the solution, searching for the solution of an objective problem is concerned is that there is a mapping for every decision vector to an objective vector. So, is mapping is there. So, if we consider another decision vector and then there will be another objective function, it is like this. So, there is a mapping from this space to this space, and out of this mapping we have to select the best mapping in the sense that this objective vector will give the optimum value. So, this problem essentially is basically mapping from decision space to an objective space, and that is the searching the procedure or the searching policy should be to find the best map. Now, more mathematically again we can define it, so that we can discuss the next discussion more in an understandable manner. So, basically the idea is that the decision space, as we have mentioned earlier, is basically the solution region, and out of the solution region there is a subset, we say that it is x bar. So, x is basically the solution space, whereas x bar is a subset of region, because all solutions may not be the feasible solution. So, we have to consider the solution x bar. So, x bar belongs to x. Now, so if we consider this x bar and any point, say this one x bar into this feasible solution region, which basically satisfies all the constant that is there in the MOOP specification, then is called a feasible solution. So, x constitute of many solutions. So, it is basically in the domain of decision space, all these are the solutions, all the possible values, but we have to consider only few things, which basically, and if this is the x and this is x bar, then this basically called the feasible region and the feasible solution. So, it is the idea is that we have to find all the values which are the feasible solution first, and out of these feasible solutions we have to select a particular solution, and this particular solution we denote as x bar star. So, x bar star satisfies some constant which is mentioned here. So, again we can explain it like this: for all x bar in x bar, that means for all feasible solution in the region of feasible solution, and there exists a particular solution which we denote as star, x bar star belongs to this x bar, such that f I x I bar should be less than or equals to f I x bar, if we consider the minimization case. If we consider maximization case, then this will be greater than or equals to this one. That means, for the values of this x bar and for the values of x star bar, so this objective function should be always less than any values in the solution space. So, if the solution space contains the m number of solutions. So, here x star bar is called an optimum solution, or it is basically a desirable solution. So, mapping therefore comes into this picture. So, from the set of all design parameters values, we basically obtain the solution space. From the solution space, we have to decide the feasible solution, and out of all the feasible solution, we have to select one solution which is called the optimum solution or desirable solution. That means, we have to search the design space for which values x will be a feasible solution, and from all the feasible solution we have to search a value which will give us a desirable solution. So, this is the concept that is there in case of multi objective optimization problem solving. and now we will discuss about few things are involved. Now, the first question that is here. So, if we know the single objective optimization problem solving using genetic algorithm, then why we should consider the different what is called the procedure or different techniques or different principles to solve the MOOP problem. Now, there are definitely many differences between the single objective optimization problem and multi objective optimization problem. So, here in these slides I have listed few differences. Now, the first, in a single objective optimization problem that we have learned so far, there the task is to find typically one solution which optimize the only one objective function, and in contrast in case of MOOP problem, our objective is to not only a single objective function, rather two or more objective function to be optimized. And when there are two or more objective functions, this means that it leads to two or more search points, in contrast to the single objective function where only one search point. So, they are because the different search point related to the different objective function. So, these are the basically constitute an objective vectors or output vectors we can say, and then we have to select out of many search point we have to select one search point. And then optimizing each objective individually, it is no issue. However, optimizing the entire what is called the considering all the objective function, putting together and then finding a global optimization is in fact a non-trivial task. Now, we can explain how this become a non-trivial task. That can be explained with an example. Here, if we see the two graphs, in the left side of the graphs we show the search space for a single objective function, and it is as usual. So, it is basically if we have to find a minimum solution, then it is the point that can be searched to find it, or if it is a maximization problem, then this point can be searched to find it. So, the single objective function is concerned is only one objective function, this is the search space, and for each search space we can find all the solutions and then ultimately find either maximum, global maximum or global minimum value. So, this is a simple problem, and we have learned about how GA can be applied to search the entire search space. Now, on the other hand, in case of multiple objective function, in the right part of the graph, if we see this graph little bit carefully, we see that we have plotted the objective functions value with respect to the search space, and the different the curves with different colors basically represents a different function like f1, f2, f3 and f4. And if we see it, then it is easily visible, it is easily understandable that the different objective function has their different points for which the minimum and maximum occurs. For example, in case of function f1, if we see the minimum, so this is the minimum value. On the other hand, if we consider the function f2, then the minimum value is here. So, this point, if this one is the solution space, then this one is the solution space there. Now, again for f3, if we consider this minimum value, maybe it is here. So, solution space there, and similarly for f4 we can find the solution space here. So, this one. Now, what we have conclude from there is that for the different objective function, if it is taken into consideration, then their solution space will be anywhere in this region. That means, in case of single objective function, if only one search point is there, but here the number of search points are there. All search points are related to search point related to the optimum value with respect to a particular objective function. Now, here the question is that out of this search point, which points should be taken in order to consider the multiple objective function optimization. So, definitely it is neither this solution or this solution or this solution, we have to select out of these one only one solution in fact. Now, which solution needs to be selected and how these solutions can be explored, this is the issue. One issue is that single objective is very fast to do it, but as is number of objective function is involved, it is obviously the multiple cost will involved in order to optimize this one. So, the traditional genetic algorithm that we have learned is not sufficient to solve this objective function. In fact, so we have to study a totally different concept to solve the MOOP problems, multiple objective optimization problem. And this is because there are some objectives which are conflicting in nature, because if we select this one solution, then other with respect to other objective function, this may not be solution. I can give an example to understand this concept more clearly. So, here one example I can see. So, these are the again with respect to two objective function f1 and f2, and how the different solutions are there in order to solve the values, it is there. So, there is a one solution, 2, 3, 4, 5, these are the solutions. Now, we can see if we consider this is the solution 1 and it is a minimization problem, then definitely this solution is preferable both with respect to f1 and f2. No, so this is a maximization, then means that this solution 1 is preferable with respect to f1. However, this solution is not preferable with respect to f2. On the other hand, if we consider this solution, this is preferable with respect to f2 because it gives the maximum value for f2. However, it gives the worst value for f1. That means, so it has one what is called the point is good, but other point is bad. Similarly, this one, and here 2, 3, 4 neither f1 is good nor f2 is good. So, this is the concept is called the conflicting objective function. So, objective functions are conflicting, f1 conflicts with f2 and vice versa. So, the same things which is mentioned here, it is shown here. So, these are the fine. If we consider this is the search space, then with respect to this search space, this is satisfiable, but this is not acceptable. Now, so it is like this. So, usually in case of multi-objective optimization problem solving, the objectives are conflicting in nature, and therefore, finding a unique solution out of these different values of the objective function is a tedious job. Now, as another example, so usually there may be some situations, if we are very much fortunate enough, then we can find a unique solution to solve where both objective functions are satisfying without any conflict. For example, here, so suppose f1 and f2 both are to be minimized. Now, if it is a minimization problem with respect to all the objectives, and these are the solutions, suppose. So, these are the solutions, and out of which so many solutions we can see one particular solution which is comparable to any other solution in this solution space. Now, this solution satisfies, or it is basically a desirable solution because it minimizes both f1 and as well as f2. So, in this case, this is a solution which is non-conflicting. Now, this solution is called ideal solution, and the situation where we can get this kind of scenario is called the ideal situation. So, usually ideal situation is very far from the real solution. In fact, it is observed that most of the objective functions in case of multiple objective problem solving, the solution is like this kind of things are there. So, here basically these are the solution region, solution space, and out of the solution space we can find some solution. It is this kind of solution actually, which is basically neither superior to anyone. For example, if we consider this one and minimization, if we both f1 and f2, then okay, it is good with respect to f1, but not good with respect to f2. Similarly, it is not so good with it may be good with respect to f1, but not good with similarly this is one is good with respect to f2, but not with respect to f1. But so what I want to say is that all the solutions that is here in this line, they are the boundary, you can say, they are any one solutions which lies on this boundary are neither superior to anyone. Such a solution in multiple objective optimization problem has a special importance. In fact, what is the special importance is that if this is the solutions we can find from the search space, then we have to take or we have to select one solution from there, or all solutions are acceptable. although it is not ideal solution. So, such a solution particularly in the theory of MOOP optimization problem is called the Pareto optimal solution, means a Pareto solution, means all the solutions are okay, we have to consider in order to decide your own solution. Okay, we will discuss about the concept of Pareto solution and then Pareto optimum solution not in this lecture, in other lectures in due time. Now, let us see if we want to solve the genetic algorithm. Basically our objective is basically to apply genetic algorithm to solve multiple objective function multiple objective optimization problem. So, idea or the framework that is used is basically same as the framework we have considered to solve single objective function. That is one important point, and I mean good point to learn it, so that the same framework can be applied. However, in the framework we have to do little bit different tactics or the different techniques to be followed. Anyway, so the idea, the basic task that is there in case of genetic algorithm is also followed here, namely initial population creation and then selection and then reproduction, and this is the loop between the selection and then reproduction producing the next generation and so on so on. But the difference is there. Difference is that whatever the method that we have discussed for the selection that is there in case of single objective optimization is not allowed or not applicable. Mainly these selection operations are to be fine tuned so far the solving multiple objective optimization problem is concerned using genetic algorithm. So, solving MOOP problem using genetic algorithm, basically the idea is that how the different tactics or procedure that can be used to use in the selection procedure, and therefore, the fitness assignment concept there because it is basically to assign the fitness so that we can lead to a better search there. So, these are the things that we will learn it. Now, I am telling you again, okay, let me clear one more thing is that, so GA is the one approach. Parallel to GA, there are many other approach in the line also to help us to solve multiple objective optimization problems like simulated annealing and colony optimization problem, particle soil optimization problem, taboo search and like this. So, all these things are the many theory, many techniques, many concepts are there, but here we will limit our discussion to the genetic algorithm based approach. Now, so far the genetic algorithm based approach is concerned, there are maybe two broad techniques. One is called the a priori approach and another is called the posteriori approach. Now, we will discuss about the two techniques in brief and then what is the procedure that is followed there. Now, here is basically the flow of the a priori approach. It is easy to understand. So, this is basically the problem, your MOOP problem, where m number of objectives are to be optimized. Now, in this approach it is called the a priori approach because it follow certain high level information. Now, what is exactly the high level information I will discuss in this lecture within a 1 minute or so. Now, okay, we will understand about high level information. Now, this information basically helps you to understand one weight vector, it is there. That means, what is the weightage of the different objective function to be considered in order to decide one solution of our own from the set of solutions provided by each objective function. For example, if W1 equals to W2 equals to Wm equals to 1, then all objective functions are equally important. But if W1 is highly important than Wm, then I can give more weightage to W1 than Wm. So, these are this one. Now, in order to have the weight values, we have to follow the high level information. Then, in terms of these weights, we can express the multiple objective function as a single objective function is basically summated weighted form W1 F1 plus W2 F2 plus Wm Fm. So, this basically gives the m. So, here basically what is our tricks is that considering the multiple objective optimization problem and transforming this into a single objective optimization problem in terms of the weight vectors. Then if it is a single objective function, then there is no issue, we can apply our traditional genetic algorithm on this and then find the solution. So, this is the a priori approach, and then we will discuss about the another approach, it is called the posteriori approach. That means, we need the information, but at a later stage. It is as usual in case of objective function. This is the problem statement. This is basically ideal multi-objective optimization problem. This is a new thing, we have to think about it. That means, it will give you the way how the multi-objective optimization problem can be solved. Now, if we solve it, right, for example, one simple idea about ideal multi-objective, you just solve one objective function at a time. So, this means that it will give you a number of what is called the solutions, as we have learned about it. So, the solution is called the Pareto solutions or Pareto optimum solutions. Then we use these Pareto solutions and passes through one high level information, because we have to see, this will give you a large number of solutions and we have to select only one solution from there, and then the high level informations can be used to select a particular solution, that is the desirable solution or our required solution. So, these are the two approach that is there, and now I will discuss about idea about so is basically high level information. I can discuss the concept of high level information with an example. Say suppose you have to purchase a car, and there are two objectives, of course, the cost and then comfort. That means, you have to purchase a car with a minimum what is called the cost involved and then maximum comfort possible from the car. Now, if you visit many cars, those are there in the car markets, then then you can find a number of solutions there. For every car have their own cost as well as own comfort. So, here we have given few examples. So, 5 solutions suppose we have surveyed, and then these are the solution like this one, out of which this car is good so far the cost is concerned, but not for the comfort, but this car is so far the comfort is concerned, it is preferable, not for so far the cost is concerned. So, then we have to find out of this the solution is there. Now, we can follow the high level information there. Now, I will discuss about what are the high level solutions are there. So, they are high level solutions like in the context of this car purchase, what are the total finance that you can give to buy the car, or what is the fuel consumption each car, depreciation value, and in which road condition which car travels better, and then physical health of the passengers if a particular car is used, and then social status and all these things. So, these are the different high level information. If you take into consideration above the solution that you have obtained, then it will help you to decide the right solutions or desirable solution. So, high level solution regarding this thing we will learn a lot whenever we discuss more theory about it. So, this is the concept of multiple objective function that we have covered in today's class. In the next class, we will discuss many theory and then some treatment, and then how to solve these problems in a more pragmatic way we will discuss in the next class. Okay, thank you very much.